We're going live. Oh, all right. Hello, everyone. Welcome back to class. Yes. We are here. We are back at class. The time has come. I have been having some trouble with my audio, so hopefully everything goes okay. But if there are problems, please just let me know in the chat, and I will do my best. I need to remember to keep my voice up, or else my mic keeps cutting out. I think there's a problem with my filters that I've never had before, so that's great. Anyway, I'm going to give a little time for people to drop in. Please don't mind this horrible doodle. I have my tablet today, and PowerPoint, there's a reason that PowerPoint isn't typically used as an art program. It's very difficult to draw in, if you can't tell. But I do want to at least have the ability to like draw on the slides and things like that. So I'm doing things a little differently today, this class, than I did last time. So I was practicing. And you can see how well that went from that abomination above me. Oh, all right, I should get rid of this. Yeah, I'll keep it. It's only one slide. What's the worst that could happen? Terrifying things, presumably, but you know, it'll be okay. We'll be fine. Oh, I made a mistake, but that's okay. All right, anyway, here we go. So, today, we are talking about frequencies and measures of central tendency. I think I summarized it in like the thumbnail and stuff as different ways of summarizing data, which is more or less what it is. We're talking about ways of summarizing data visually and ways of summarizing data through numbers, through statistics, or, you know, parameters if we're talking populations. So let's get rolling. I'm gonna make myself a little smaller. Get a little smaller so I don't get too much in the way of the slides. There, I think that should be fine. Hopefully. Okay. So, first let's start with reviewing a little bit of what we talked about last class on Monday. We talked about 3 different types of data: nominal data, ordinal data, interval data, and ratio data. Nominal data was categories that had no particular order to them. Ordinal data was data where there was a particular order to our data. So this can be things like rankings and stuff, but the size of the units isn't always the same. The space between first and second place in a race isn't necessarily the same amount of time as between second and third. Like, one of those is a better place in the race, yes, so there is an order to it, but the units aren't the same size. The gaps between spaces isn't the same. Interval data was data that does have all the units are the same size, and some units are worth more, some are worth less. So there is an inherent order to it. So good examples of interval data are Celsius and Fahrenheit as measures of temperature. They have an order to them. 1 degree Celsius or 1 degree Fahrenheit is 1 degree no matter what. But interval has a weird property that it doesn't have a rational 0 point. A 0 on the Celsius or Fahrenheit scale doesn't necessarily mean 0 temperature. The 0 is just kind of arbitrary. It just means that it's cold. It doesn't mean 0 of the thing that scale is measuring. Then we have ratio data. Ratio data has an order. All the units are the same size, and it has a rational 0 point. 0 on a ratio scale does mean 0 of the things that it's measuring. So for example, inches or pounds or grams or whatever, things like that. The way that I remember the difference between interval and ratio is ratio is the one that has a rational 0 point, and there's an O in the word, which kind of looks like a 0. Interval does not have a rational 0 point, and it doesn't have an O in it. So it doesn't have a so-called 0 in that word. We also talked about 2 different sort of types of statistics. We talked about descriptive statistics, which are statistics that's just trying to summarize data. It's trying to take a whole bunch of numbers and come up with 1 or 2 numbers that summarize that entire spreadsheet. Inferential statistics are statistics where we're asking a question and trying to get an answer. So that would be like hypothesis tests, trying to figure out if a new type of therapy helps treat some sort of symptom or something along those lines. So descriptive, you're just summarizing. Inferential, you're trying to answer a question. And today, like we will be for the first few weeks, we are just going to be focusing on descriptive statistics. We won't get to inferential statistics for a few weeks yet. We also talked about some vocabulary. We talked about populations. So a population is every single individual in whatever group you're studying. For example, if I'm studying anime fans, it's every single anime fan on Earth. If I'm studying people with depression, it's every single person with depression on Earth. So population, every single thing. In my area, social psychology, we tend to be interested in the so-called average human. So a lot of the time, our population is every single living human being on the planet. Populations are summarized by numbers called parameters. So the, say, average height of the entire population of Norway would be described as by a population parameter. The average there would be called a parameter. You don't really see this that often because it's really, 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 really unusual that you get an entire population. Then we have samples. Samples are a small chunk of the population. They're a group of people or a group of things that you have hopefully randomly selected from the population, and you're using them to kind of represent the population as a whole. And if you take the average of, say, data from that, that would be a statistic. So let's say I take the average height of 20 people from Norway. That average is a statistic. It's summarizing data from a sample. Summaries of data from a population, those are called parameters. But again, you don't really see parameters too often. It's highly, highly unusual. It's super rare that we can get an entire population. Like, no psychologist has the resources to give a survey to every single living human being on the planet Earth. That's just not a thing that we can do. I don't even know if anyone could do that, much less like some random psychologist, right? And then we also finally talked about sampling error. Sampling error is, like I said, we usually want to study populations. We want to draw conclusions about humanity as a whole, or creatures as a whole, or whatever it is we're studying. But it's impossible to get population data. So we have to settle for data from a sample, so a small section of the population. Sampling error is the difference between the number we're trying to estimate, the population value, and the number that we actually get from our sample. That's sampling error. The fact that samples will always be different from the population. No small chunk of a population will ever be a perfect representation of the entire population. So that's more or less what we went over last lecture, if you needed a bit of review. Today, we're starting off talking about frequency distributions. We'll talk about regular frequency distributions, we'll talk about grouped frequency distributions, and cumulative frequency distributions. Do I have something else? And histograms! Histograms are kind of a special case of all these kinds of things. There's frequency distributions, and histograms are a certain type of frequency distribution. So we're going to be talking about these. That's right, we are starting out talking about graphs today. Like I said, visually summarizing data. So here is an example of a data visualization or a frequency distribution. This is data from my anime list. This data set's kind of old. I think it's from 2019 or so. But this is summarizing how many anime were in their database that fit each category. We've got anime movies, we have anime music videos, we have ONAs, we have OVAs, we have special episodes, and we have TV anime. So this is a graph that just summarizes how many anime on my anime list fit into each category. Now I'm going to start off, before we get into graphs, let's talk about tables. This is something called a frequency table. So frequency is just how often something appears, and this table is trying to summarize that. Let's say I have the ratings for 12 anime. So my anime list uses a rating out of 10. People can rate how good or how bad they think an anime is out of 10. And I have the ratings out of 10 for 12 different anime here. 8, 4, 9, 7, 6, 10, 8, 9, 7, 7, blah, 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 blah. This table is trying to summarize that data. Here we have X values. X typically refers to just a score in a data set. So these are all the possible values of all the scores in the data set. Some people, or some anime, were rated 10s, so that's a value. Some were rated 9s, so that's a value. Some were rated 8, that's a value, and so on. And I guess theoretically this could go all the way to 1, but no anime in this data set were rated below 5. This column here, the F stands for frequency. It's counting how many anime got that rating. So you can see the frequency of 10 is 3. And we look at our list of anime ratings, there are 3 10s in there. That's what this is saying. 3 anime in our list got a 10 out of 10. 1 anime in our list got a 9 out of 10. Oh, it looks like I actually have 2 9s in here. I might have messed up on this table a little bit. We have 2 9s. And 2 8s. 2 9s and 2 8s. It's okay to make mistakes, as long as we catch them. So we had 2 9s. 2 8s, we had 3 10s, we have 1 7. No, we have 3 7. Oh my gosh, this is really bad. We have 3 7s. We're fixing this in real time. Look at us go. How many 6s do we have? We only have 1 6, so this should be a 1. And, oh my goodness, we don't even have a 5. We have a 4. So we have 1 4. Sorry about that. That could have gone better. And let's see how many we have total. I think it should be 12. We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, and if we count how many anime ratings we have here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And then this is the percent out of that we should have. These numbers probably aren't accurate considering that these weren't, so let's test this out. The percent is calculated as the frequency so the number of times that score showed up, or the frequency, divided by the total number of scores. So out of all 12 scores, how many anime were rated a 10? So I'm pulling out my calculator here because I cannot do math in my head. We had 3 anime that scored a 10 out of 12 total anime. So that's 3 divided by 12. Indeed, 25% of the anime scored 10 out of 10. Next, we have 2 9s. Here's 1 9. Here's the second 9. So 2 divided by 12, because 2 of the anime scored 9 out of 10. That's 16%. Maybe it's good that we're doing it this way. You can see where these numbers are coming from here. Next, we had 2 8s. We had this one and this one. 2 of the ratings out of the 12 total ratings were 8. So that's 2 divided by 12. About 16% of the ratings were 8. 16% of the anime in this sample got an 8. Then we have 3 anime got a 7. So 3 divided by 12. About 25% of the anime got a 7 out of 10. And then for the next 2, we have 1 6 and 1 4. So 1 divided by 12. About 8%, I'm rounding, it's 8.33 repeating, but about 8% of the anime got a 6 out of 10, and 8% of the anime represented in the set got a 4 out of 10. And this should all add up to 100%. Oh, man. Sorry for that confusion. There we go. So this is a frequency table. It tells you all of the values that are in your list, 10, 9, 8, 7, 6, and 4. It tells you how often each value appeared. There were 3 10s, there were 2 9s, there were 2 8s, 3 7s, 1 6, and 1 4. And we also have this extra column here that tells you what percent of the total ratings had that value. 25% of the anime had a 10 out of 10, 16% had a 9 out of 10, 16% had an 8 out of 10, 25% had a 7 out of 10, 8% had a 6 out of 10, and 8% had a 4 out of 10. This number on the bottom, N, is the total sample size. It's how many anime there were total, or how many data points you had total in here. Oh, there we go. So that's what that N stands for, and this 100% is like the total percentage. All of these percentages should add up to 100 because it's accounting for the total percentage. Now, This is ratings on a scale of 1 to 10, right? Just to review some of what we did last time, we talked about different scales of measurement. The cropping on this is a bit weird. But we looked at different scales of measurement. Can anyone guess? And I don't think there's anyone in chat right now, and that's okay. But I was wondering if anyone would be able to guess, just you can think to yourself, which scale of measurement is this on? Is this an ordinal scale, where there is an order to these things? Some things are greater than others, but the size of the units isn't necessarily always equal. Is this a nominal scale, where there is no inherent order to this scale? Or is this an interval or ratio scale, where there is an inherent order and all the units are the same size? I give you a minute to think about that. This is an ordinal scale. So an anime that is a 10 out of 10 is obviously the highest rated anime, or one of the highest rated anime on this list, and an anime that's a 4 out of 10 was probably pretty bad. So some of these numbers are inherently higher than others. There is an inherent order to this. 1, then 2, then 3, then 4. You can place it in an inherent order. But the weird thing about this is things like subjective ratings, like quality of an anime or how depressed you are on a scale of 1 to 5, those tend to be ordinal. We cannot guarantee that the difference between a 1 out of 10 anime and a 2 out of 10 anime is the same as the difference as a 7 out of 10 anime and an 8 out of 10 anime. We can't guarantee that those units are the same size. So we would consider this an ordinal scale, at least as far as, statistics and data analysis is concerned. So here are two different ways of graphing the frequency table that I just showed you. On the x-axis here, we have the anime rating. And I think this is an old version of the data. I must have failed to update it for this. On the x-axis, we have the anime rating. It was rated a 5, a 6, 7, 8, 9, 10, and so on. And on the y-axis, on this left one, we have frequency, how often that appeared. So let's say this is a different set of 12 anime ratings. In this set, there was one anime that was rated a 5, 3 anime that were rated a 6, 1 that was rated a 7, 3 that were rated an 8, 1 that was rated a 9, and 3 that were rated 10. On the right, we have the same graph. I mean, it looks pretty similar. The only difference is that instead of the y-axis just counting how many anime were in that category, it's the percent of the total anime that were in that category. So about 8% got a 5 out of 10, about 25% got a 6 out of 10, and so on. They're displaying the same data. It's just the one on the left is displaying it as the total number. The one on the right is displaying it as a percentage. Left is frequency, right is a percentage. I definitely always recommend you pay attention to the y-axis to tell if you're looking at this is how common it was, or this is the percent of the total it was, because the graphs themselves will look pretty similar. It's just the number on the y-axis that will look different. So here's another example. Here we have another frequency distribution. On the x-axis, we have the genre of each anime. On the y-axis, we have the number of anime in the MyAnimeList database from this data set that I have that fell into that genre. I think I did this as like the first genre listed on their page. Or it might have been just, did it have this genre listed? Yeah, it was this one of the genres listed. And then we have a table here. So each row is a different genre of anime. We have action, comedy, drama, fantasy, romance, school. And then we have the sample size for each. So 2,845 were action, 4,645 were comedy, 2,016 were drama, 2,309 were fantasy, 1,464 were romance, and 1,220 were school. And you can see that in this graph. You can see comedy was the most common. It had the highest number of anime. School was the least common. There were relatively few anime that took place in a school, but that's still a lot of anime. That's still over 1,000 anime. Now, another bit of review from last class. What scale are these data on? Nominal, ordinal, or an interval or ratio scale? Again, nominal is just categories with no inherent order to them. You can put them in any order. Ordinal, these are categories, but they do have an inherent order to them. So you can place them in some sort of natural order that makes sense, but the space between the categories, the space between the units isn't necessarily always equal. Then, interval and ratio, I'm kind of lumping them together because they're pretty similar. These ones do have an inherent order to them, and all the units are the same size. So, I should make myself a bit smaller, or at least move myself around a bit, just so you can see this a bit better. Any guesses on what kind of scale this is? You don't have to say it out loud, just try and think in your head. What type of scale is this? Is this nominal, ordinal, or interval ratio? Or interval or ratio? This scale, first off, this scale's nominal. Genre is a nominal scale. There is no reason that these have any particular order to them. They don't need to be placed in any particular order. I just happen to place them in alphabetical order, but I easily could have put them in order of most common, or easily could have put them in the order of highest rated. There's no reason I had to put them in the order they're in. They're categories and they don't have an order. So this is a nominal scale. Where's my cursor? Oh. Nominal scale, let me draw. These. It's just, yes, you know you want to let me draw on it. Well, it's a nominal scale. That's the point. The point is that it is indeed a nominal scale. Now, you'll notice something about this graph that is different from the last graph. The last slide's graph, the bars are touching. So it's still showing similar data. It's still showing how many things fit into each, or how many things there were in each category. In this case, the category is a rating out of 10 stars. In this case, the category is genre. But in this one up here, the bars are touching. And in this one here, the bars are not touching. Wonder why that might be. There's a very good reason why the bars are touching in the other graph, but they aren't touching in this graph. I'm curious if anyone has any guesses why that might. Is my mic cutting in and out? Oh dear. Yes, there's a non-stylistic choice. There is a reason why the bars are touching here, but the bars are not touching here. Yes, histogram! Yes! This is not technically a histogram, or sorry, this is a histogram. This is a histogram. In this case, our x-axis is like, it's a variable where there is some continuity. Higher numbers mean higher things. There is a reason that it is in this order. So we can sort of infer patterns as the anime rating goes up. At least in this case, the anime rating tends to sort of go up and down, up and down. Here, though, I could have put these bars in any order I wanted. This is a nominal variable. I don't want to imply that there's some continuity where the number of anime is going up and then down as you move across genre, because I could have made these bars look however I wanted just by reordering those categories. There's no reason the categories have to be in this order. This isn't some kind of, curvilinear trend that we've got going on here. It's just arbitrary. So for things that don't have, so for like nominal data, generally speaking, we do not want the bars to touch because we don't want to imply that there's some sort of pattern going on here when really there isn't. Here, we can do that because these bars are in their sort of natural or specific order. Here, we do not want to do that. So we don't want the bars to touch when our variable is nominal. We don't want to imply anything that's not actually there. People forget this a lot, though. If you look in a lot of journals, people will make bars touch or not touch just kind of arbitrarily. But I'm trying to teach you to be better than, some of the things that I see out in the wild. And I get why people forget, but there's a reason. There's a reason. Okay. We can also graph the same data with percent. So before, I was graphing it by just sheer number of how many things fall into this particular category. Here, we can also graph it by percent. So there was a total of 14,449 anime in this data set that had genres. And I can say, well, 20%, I can calculate that, 2,845 divided by the total number is about 20%. 20% were action, 32% were comedy, 14% were drama, etc. It's the same data. I'm just displaying it as percentage instead of just raw count. You can do either. It's totally fine. Whatever suits. I think personally, for when you're dealing with numbers this big, percentages are a bit easier for the human brain to digest. If it's smaller numbers, like this, maybe just the raw numbers, the raw frequencies is probably easier to digest. And probably makes a lot more sense in general. All right, another type of frequency distribution. Here we have something called a grouped frequency distribution. This is when you've got a really, 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 really big scale. Shocked at fantasy not being number one with the fire hose of isekai stuff out there. Yeah, well, this is the stuff that I used for... No, it's not that. Yeah, I think part of it is that this data set, I believe the way that I process this data is anime have multiple genres on my anime list. They can be listed under multiple. So it's not like this one is only, the fantasy is only categorized as fantasy and comedy is also only categorized as comedy. You might have some that count for both. So the comedy bar is counting not only comedy that aren't fantasy, but comedy that also are fantasy. So it's like, there's a bunch of stuff being counted twice in here. It's kind of messy. This is just how often each genre appeared in that list. But, because anime have multiple genres in them, it gets a bit gross. It's not the cleanest thing in the world. And, there's a whole bunch of like slice of life stuff out there. That's another big section of anime that, I guess back when I started to get into anime, that wasn't localized as much. It was mostly fantasy stuff that got localized and, like brought over to English-speaking countries back in the day. This data set's also from 2019. Isekai animes really started to blow up around 2019 to the levels that we're seeing now, so it's possible that this data just isn't recent enough for that fantasy to be quite as high as we'd expect it to be, given the market saturation that isekai has right now. So it could be a product of its time, context and all that. It's fun to think about, though. I'll have to look at that. Anyway. All right, grouped frequency distributions, another way of displaying data. Sometimes you have really, really big scales. This happens when people are working with things like reaction time in milliseconds, or in this case, I have Rotten Tomatoes ratings. If you're not familiar, Rotten Tomatoes is a website that you can look at to see how people feel about movies. And the Rotten Tomatoes scores are what percentage of audience members liked that movie. 0% being everybody hated that movie, not a single person liked it. 100% meaning every single person who saw that movie liked that movie. So higher percentages are better, lower percentages are worse. But of course, it kind of really sucks. It's not very nice to look at a bar graph or a frequency distribution that has literally 100 bars on it. That can be kind of hard to process, and the difference between a 91 and a 92 probably isn't that big of a difference that you're terribly interested in. So in this case, we might do a grouped frequency distribution, where say I group this into 10s. This many movies got a Rotten Tomatoes score between 0 and 10. This many got it between 11 and 20. This many got it between 21 and 30, and so on and so on. The height of each bar still represents how common that thing is, so you can tell the tallest bars and the most common Rotten Tomatoes scores were in the 80s, 70s, and 80s. But now we're just grouping it together into categories instead of letting each individual Rotten Tomatoes rating have its own bar, just to make it easier to look at, easier to process. So yeah, that's another thing you can do. This is, generally speaking, these are called histograms. Technically, when you're working with nominal data, so data that doesn't have an order to it, that's not a histogram. Histograms are technically supposed to be only interval ratio data, but the big point of histograms is that the height of the bar represents how common that thing is. Shorter bars are rare, taller bars are more common. That's a histogram. It's a special type of frequency distribution where specifically you're working with interval or ratio data, though people absolutely do histograms with ordinal data too. Technically, it's not supposed to be called a histogram, it's just a frequency distribution, but In psychology, we use a lot of ordinal data, so we call them histograms anyway. And I don't think anyone, unless they were being really, really, like, pedantic or, like, really well actually at you, would fault you for calling something with ordinal data a histogram. I've seen people call... Anyway, I'm getting away from myself. Yeah, so technically the difference is histograms, the height of each is interval ratio data. Bar charts. Bar charts are when the data is discrete, most often when the data is nominal. You can think it works the same as a histogram. The height of the bar still represents how common the thing is. We just use a different term for it. If you don't want to worry about those different terms, it's probably not worth worrying about it all that much. Most people won't get up in arms about this. The main thing that I care about you understanding is taller bars mean more of that thing, shorter bars mean less of that thing. As long as you can read this, understand what these bars mean and what their heights mean, we're good. I think that's all that you'll really need going out in the world. All right. Oh, what have I done? There we go. Okay. You might also see graphs called frequency polygons. This is a frequency polygon. So let's say I'm looking at grades and the number of students who got each grade. Here on the x-axis, we have grade. We have students who scored in the 60s, the 70s, the 80s, and the 90s. So this is sort of another grouped thing. And on the y-axis, we have how many students got that score. And then we have kind of a midpoint. This is sort of the average score that students got. We could represent this with a bar chart. We could draw bars here and say, oh, there were 3 people who got a 60. There were 6, and I can tell this, but I'm looking at the point and going back to the y-axis, 6 people got a 70. 8 people got an 80. And about 5 people got a 90. So it's between 4 and 6. 5 people got a 90 or so. We could display it as a bar chart. We can also display it as a frequency polygon. It makes it a bit easier to see trends. So here I can see most students were getting a B. Most students were getting 80s. And then grades became less common as you moved away from 80. Relatively few people got only 3 people got a 60. It's pretty rare. Most people were hovering around 80, and most of them were within 10 points of a B, within 10 points of an 80. So it lets you see trends, and it's a bit easier than like bar charts where you would have to draw that line over it or imagine that trend line. Now, so we've got this data. It's your grade. Just to review from last time, would you think that this is ordinal, nominal, or interval or ratio data? It's the big question. This is actually a weird, complicated question, because depending on how you interpret it, you might get a different answer. But I'd say the simplest answer, personally, is it's probably ratio data. If we're talking about like the percentage of questions you got right out of 0 to 100, it's probably ratio data. There is a natural 0. You could get 0 questions right. I've never actually seen that happen. But, theoretically, it's possible. You could get all the questions right. And 1 point is 1 point no matter what. So this is probably ratio data. We just grouped it to make it easier to look at. So that's a polygon. By the way, you wouldn't want to do polygons with nominal data for exactly the same reason as you wouldn't want to do, you don't want the bars touching on a nominal data histogram, or a nominal data frequency distribution. Because that would imply there's some continuity there. If it's nominal data, I could have put these in any order I wanted to. We don't want to imply there's some sort of trend. But these are nice. It's nice to be able to look at the shape of frequency distributions, and there's a couple different shapes that we might see if we're working with data that has an order, so like data on ordinal, interval, or ratio scale. Sometimes we'll have symmetrical distributions, where both sides from the midpoint look like a mirror image. So let's say we're talking grades. The average is an 80. About half the students got below an 80, half the students got above an 80. You can fold that over, smack, folds right over itself, perfectly symmetrical. This is a symmetrical distribution, and this type specifically is called a normal distribution. I don't know why we call it a normal distribution. I think that's more of an aspirational thing to call it, because we like it when distributions look this way for like statistics reasons that we'll talk about later. But this is a symmetrical distribution. Fold it in half, it's symmetrical. We'll also see things like unimodal and bimodal distributions. So we'll talk about this a bit later, but the mode is the most common value in a data set. Unimodal distributions, this would be a unimodal distribution. There's one highest point. There's one most common score, say a B. A bimodal distribution would be a distribution that has two highest points. Let's say a bunch of students got an 80 and a bunch of students got a 60. Maybe I gave the same test to a bunch of kindergartners versus a bunch of college freshmen or something like that, you know? So this has two modes. There are two most common scores. That's a bimodal distribution. We also have skewed distributions. This means most of the scores are at one end of the scale. And there's two different types of skew, talking sort of generally. There's a negative skew. Oh, I was doing it again. It's doing the weird thing again. Negative skew is where most of the data is on the right and very little is on the left. So you can think of it like the thin part of the distribution is pointing towards negative numbers on a number line. That's how I remember it. This is a negative skew. So most people are scoring high, very few people scoring low. Or a positively skewed distribution, where most people are scoring really low, very few people are scoring very high. So the tail, the skinny part of the distribution, where very, very few people are, is pointing towards more positive numbers on a number line. That's how I remember. So here's nicer pictures that weren't drawn by me. Up here we have a unimodal symmetrical distribution. There's one most common score. Remember, the higher parts of the distribution are the things that are the most common. The lower parts are the things that are the least common. So let's say there's 1, 2, 3, 4, 5 people with this score, you know? This is a bimodal distribution. Again, if you fold it in half, it's symmetrical. But there are two most common scores, here and here. And then we have our skewed distributions. This is a distribution with a positive skew. Most of the scores are on the lower end of your scale. So your most common stuff is on the lower end of the scale. Very few people are on the higher end of the scale. And negatively skewed, most of your the scores are on the higher end of the scale, relatively few on the lower end of the scale. And you can see that positively skewed distribution, its tail is pointing to the right. Negatively skewed, the tail is pointing to the left. Just to give you a little thing on language, why do I call it the tail? So the way that we think of distributions is kind of like, I don't know if this is how other people think about it, but we think of it as a creature. So I'm going to make it a cat because I can. This is a cat distribution. This part here, the bigger part of the distribution, is what we call the body of the distribution. And then the thinner part of the distribution, we call it the tail. So if it helps to kind of imagine these distributions as creatures with tails, maybe that will help you with the language here. This is the body, this is the tail. And these symmetrical ones have two tails. I guess in like Japanese terms, they're, if we stick with the cat thing, they're nekomata, they're a two-tailed cat. So here's your body, here's a tail, and here's another tail. Da-da-da-da! I need to make a plush of these things. Strange little distribution creatures. Anyway. So let's talk about examples of these out in the real world. The normal distribution, or the normal curve, there's a bunch of different examples of this. I honestly don't like using IQ that much because it's not a really great measure of much other than how good you are at taking IQ tests. It has some problems with like cultural generalizability and like other things, but yeah, distribution creature, I would love that. Even if it's not merch, I might make one for myself. But yeah, IQ, a lot of standardized tests like the SAT, the ACT, the GRE. There are medical tests. There's something called the PROMIS, PROMIS. all these standardized tests tend to standardize to a normal distribution. They want a symmetrical distribution where the mean is right in the middle, and then there are very few people the further away from the mean you get in either direction. Symmetric bimodal distribution, an example of this might be height. So if you look at the average heights of people, yeah, that's fair. I would love to hear your thoughts on the IQ test. Yeah, right. We should go and do an IQ takedown stream. I would love to do that. I have so many problems with it. Anyway, or maybe I should just one day I'll go on a rant. I think I already kind of did in one of my previous videos, like briefly about it. But anyway. This is a bimodal distribution. Height is like that. There's, so people who are designated women at birth, or female at birth, their average height in the US, which is the one where I just happen to know the average heights, is around 5'5", with some people who are shorter than that, some people who are taller than that. People who are designated male at birth, their average height in the US tends to be about 5'10", some are shorter, some are taller, and of course, like, there are some women who are taller than 5'10", some men who are shorter than 5'5", you know, but this is how the distribution of frequency of height in the US tends to look. We have two peaks. There's a lot of people who are roughly around 5'5", a lot of people who are around 5'10", very few people who are, say, under 5 foot, very few people who are, say, over like 6'5" or something. It looks like this. This is the symmetrical bimodal distribution. You might also have things called asymmetric bimodal distribution. So you have two scores that are equally common, but it's not quite symmetrical. So let's say I have a game. I'm playing a game and it has 4 difficulty levels. I have one super easy baby difficulty level and one easy baby difficulty level. So most of those scores are high. People are getting really high scores on the super easy baby level. People are getting fairly high scores on the easy level. And then there are 2 very hard ones. Or if we're talking completion time, it might look the same. So if it's completion time, in the 2 hard ones, people are taking a long time to complete this game. In our 2 hard difficulties, and they're both equally hard, so people are just taking a really long time in general. And then for the easy difficulty, they're taking a shorter amount of time. And then in the baby easy difficulty, they're going real fast. This is the one that you want to do if you want to like speed run it or something, though maybe it wouldn't be as impressive because it's like baby difficulty. So you have a lot of completion times over here, a lot over here, but this hump is wider than this one. So it's not a symmetrical distribution. One of the bumps is wider and one of them's narrower, but you still do have 2 modes. You have 2 high points on that distribution. Then we'll have unimodal, skewed left. So this would be a negatively skewed distribution. So this would be an easy game. Let's talk about, say, your score on the game. If you're taking an easy game, or if you're doing a very easy game, a lot of people are probably getting a very high score on that game. So most people are scoring very high on this game. Very few people are scoring really low on this game. So that's a unimodal, skewed left, or negatively skewed distribution. Then we might have a very difficult game where it's skewed right, like QWOP, I think. Am I dating myself by talking about QWOP? I don't know. I tried it once and it was horrible. Or Getting Over It or something, you know? I don't know if that has a score thing, but a lot of people are getting really low scores. Very few people getting very high scores. That would be a positively skewed distribution in the real world. We also have U-shaped or inverted U distributions where most people are either scoring very low or very high, and very few people are right in the middle. You're either really good at something or really bad at something. Nobody's in the middle, or an inverted U, where pretty much everybody is around the same level. No one is exceptionally high, no one's exceptionally low on that particular thing. So those are all different shapes of distributions that frequency distributions might take, with most of them having real-life examples. One example for the U-shaped distribution, I struggle with the inverted U-shaped distribution, but one example that shows up a lot with the U-shaped distribution is belief in misinformation. So if our x-axis here is how liberal you are and how conservative you are, this is in a US context, so this, you could sort of say how Democratic you are or Republican you are. People who are very, very liberal tend to believe a lot of liberal misinformation, and people who are very, very conservative tend to believe a lot of conservative disinformation, and people who are more politically neutral or moderate don't tend to be drawn to political misinformation nearly as much. So that's the case of a U-shaped distribution. Inverted U, I honestly can't think of any examples off the top of my head, unfortunately. Oh, the slide got messy, sorry. All right, percentiles. Let's talk percentiles. Percentile ranks or scores are a score that defines your performance or somebody's score on something with respect to a norm or a reference group, which is a very fancy way of saying, how did you do or how did you score relative to everybody else who did the same thing? You see these a lot if you've ever taken a standardized test, like, again, the SAT or the ACT or the GRE or an IQ test or whatever else. Like, if you've ever taken any of these standardized tests, you probably got a percentile. This is the percentile that you're in. This is how you compare to everybody else who has taken this test. So they convey your standing relative to everyone else. It's not just like how absolutely did you get above this threshold. So like, did you get an A or a B? It's not talking about that. It's not talking about, say, the percentage of problems you got right. It's talking about how many people did you do, how many people did you score higher than? So to do this, first you need to calculate something called a cumulative frequency and then a cumulative percent, which is just the number of people up until your score, and then the percentage of people who got your score or lower. So if I'm in the 20th percentile, that means my score is higher than 20% of people who did the same thing. So let's say I get in the 20th percentile on, I'm in a Tetris tournament and my score is in the 20th percentile of Tetris players. That means I only did better than 20% of the people who were playing. 80% of the people did better than me. My percentile is 20%. I was pretty bad at Tetris. But if I'm in the 90th percentile on Tetris, I'm good. I did better than 90% of my competitors. Only 10% of people did better than me. Of course, percentiles aren't always good. Let's say I'm talking about like something like risk for spontaneous combustion. I would much rather be in the 20th percentile for risk of spontaneous combustion. I have a very, very low chance of randomly bursting into flame than in the 90th percentile of risk. But, you know, it's just how many people are at your point or lower. And that can be a good thing, it can be a bad thing, depending on exactly what you're talking about. So let's say, I think after this point, I'm gonna use a wider variety of examples, but right now I'm still stuck in my anime example phase because that's what I prepared. I watched Kaiju Number 8 recently, and it has a power scaling kind of thing, you know, on a scale from 1 to 100, how good are you in combat based on their way of measuring it, their operationalization. So let's say we're using a range. Range of unleashed combat potential is what they call it. Unleashed combat potential, with higher numbers being better, lower numbers being worse. Let's say we have 6 recruits whose combat potential is between 6 and 10. 5 recruits who are between 11 and 15. 5 who are between 16 and 20, and so on. So we have the range of unleashed combat potential they're in. How many recruits were in that particular range? The cumulative frequency. In other words, how many people, cumulative frequency is how many people are in that range or lower. So we have 20 people total. This sum is just how many people total, or how many recruits total are represented in this table. Cumulative frequency is how many are in this range or lower. So the lowest range we have is 6 through 10. That had 6 people in it. 6 people are in this range or lower. But if we move to the range of 11 to 15, 5 people are in that range. The cumulative frequency becomes 11. I want you to take a moment and think about how we got this number 11. Where you think it came. It's called cumulative frequency because you take the frequency before it, add the amount of people in the new category, and that gives you the cumulative frequency. So we had 6 people below this score, 5 people with this score. So 6 plus 5 is 11. 11 people scored in this range or lower. And then we just keep doing that. Go to the 16 to 20, 5 people scored in this range. 11 people scored lower than this range. 11 plus 5 gives us 16 people scored in this range or lower. 0 people scored in this range, so it's still 16 in this range or lower. 1 person scored in this range, so add that. 17 people were between 26 and 30 or lower. Then 3 were in this range, add that. 20 people scored between 31 through 35 or below. That's a cumulative frequency. How many people are in this range or lower? And it should add up to, the total number of people you've got, because eventually you've accounted for every single person in your sample. You can use the cumulative frequency to calculate the cumulative percent, which is the percentile. You say, okay, 6 people were in this category or lower. Out of 20 people, 6 divided by 20 is 30%. 30% of people were in this range or below. Then you do that just all the way down. 11 people were in this range or lower. 11 divided by 20 is 55%. 55% of the recruits were in this range or lower. We can go here, there's 16 for the cumulative frequency. 16 divided by 20 is 80%. 80% of people were in this range or lower, and so on. And that's how you get a percentile. By the way, this is just saying cumulative percent is equal to the cumulative frequency, this number here, divided by your total sample size, which is this number here. Just a fancy math notation way of saying the number of people till that point divided by the total number of people. That's cumulative frequency. And yeah, that is pretty much how you calculate that. That's how you calculate percentiles. So let's do a little test. If my unleashed combat power, let's say I was randomly isekai'd into the world of Kaiju number 8, and they measured my unleashed combat power, and my unleashed combat power was, say, I don't know, 24. If my unleashed combat power is 24, which percentile am I in, according to this data? What percentile is my unleashed combat potential in? Let's think. 24 is in this range, between 21 and 25. So that means my percentile is whatever is over here. That means I'm in the 80th percentile for unleashed combat potential, if my score is 24. So the answer here, 3. I'm in the 80th percentile. 80% of people were in my range or lower. That's how percentiles work. And now let's do something completely different. I promised measures of central tendency. So that's what we're going to talk about now. We're finally here. So it's not completely different. I think all of this is talking about ways to summarize data. Before we were summarizing data, as you know, like percentiles or using graphs. Now we're doing it through mean, median, and mode. Central tendency is a way to measure or summarize a set of data. So let's say you have a whole bunch of data. You have, say, the heights of 200 people. How are you going to summarize that? Well, we're going to try and come up with a single number that represents all of that data. There are 3 main measures of central tendency that you may have heard of before: the mean, the median, and the mode. The mean. This is your average of a set of scores. So when I say the average or the mean, that means exactly the same thing. I'm referring to the same thing. This is by far the single most commonly used measure of central tendency, both, inside statistics and outside of statistics. This is what people use the most, just generally, regardless of if you're being a researcher about it or if you're actually, if you're doing other things, if you're just being an everyday person, you're probably using the mean, aka the average. Technically, you're only supposed to do the mean with interval or ratio data. You shouldn't be doing this with ordinal, and you definitely cannot do it with nominal. So you shouldn't do it with ordinal. We do it with ordinal all the time. We calculate the mean of ordinal data all the time, even though we really aren't supposed to. But we can't even, it's impossible to calculate it with nominal data. Now, if I were to use the fancy notation that I'm going to be using throughout this entire series of lectures, this is how I'd write the formula for the mean, but it's exactly the same formula that you're familiar with. This sum, this just says add all the numbers in x. X is a list of numbers, divided by the total number of numbers. It's just add all the numbers together, divide them by the number of numbers. That's all. Both of these are saying the same thing. We write them slightly different to indicate whether we're calculating the mean of a population, so we have every single individual we care about, or the mean of a sample, so we only have some of the individuals in the population we care about. But it's the same thing. The process of calculating them is exactly the same. Just the notation is different. This symbol here, and we'll talk about this more later, this is called mu. It's a Greek letter, and it represents the population mean. If we're talking about a sample, we use capital M to do that. And then if we're talking about every single human being in the population, the size of the population, we use a capital N. If we're just talking about the number of people in our sample, the size of our sample, we use lowercase n. But really, when you're actually doing the math, these formulas are exactly the same, and they are exactly the same average formula that you learned when you were learning to calculate the average for the first time, which I'm hoping all of you have learned to do before. If you haven't, though, that's fine. But I might not go over it. Now, sometimes we might want to calculate something called a weighted mean. A weighted mean is when you're averaging something from two samples together. And samples have different sizes. Some samples are bigger, some samples are smaller. A weighted mean averages those two means together, taking into account the size of the samples that they came from. And I'm going to talk about why that's important. But let's say if I have, say, the average height of people in my morning class and the average height of the people in my afternoon class, and I just want to average that together to get the average height of my students, I'd probably want to do it using a weighted mean. So some examples of mean, let's say, let's go My Hero Academia with it. Let's say I'm interested in the average number of Windows All Might breaks in a day in period 1. So period 1 is 4 days long. I've got data from 1, 2, 3, 4 different days. On day 1, All Might broke 15 windows. On day 2, he broke 25. On day 3, he broke 35. And on day 4, he broke 45. To calculate the average, or the mean, all I have to do is I have to add up the data from all those days, divide by the total number of days, which was 4, and get an average of 30 windows. So in time period 1, All Might broke an average of 30 windows a day. Then we might have period 2, and in this time we have a different number of days. We have 1, 2, 3, 4, 5, 6 days. We were somehow able to observe him for a longer period of time. Day 1, he broke 10 windows. Day 2 was 20. Day 3 was 25, and so on. To calculate the average, or the mean, we do it exactly as we did before. We add together all the windows that he broke over this time period and divide by the number of days. So divided by 6. For an average of 25 windows broken. Now we might want to weight by average of time period. To do this, we use that weighted mean formula. We take 120 plus 150. By the way, these numbers, 120 is the sum of the total number of windows that he broke on day 1, or in time period 1. 150 is the sum of the total number of windows that he broke in time period 2. So we add those together first, then we add together the number of days in time period 1 and time period 2. We divide the total number of windows by the total number of days, and that gives us our weighted average. An average of 27 windows a day. And you can also write the formula for weighted average like this, but why would you? Like that looks so much more complicated and intimidating. Now you might be wondering, well, why don't we just say take that 30 windows in time period 1 and add the 25 windows and then divide that by 2? Why don't we just average the two means together that way? I mean, that's a reasonable way to do it. It's less work, probably. And the reason that we don't do it is something related to sampling error. Now, in time period 1, we only have 4 days. Our sample size is 4. In time period 2, we have 6 days. Our sample size is 6. Now, think about it this way. If I'm trying to get an idea of the population number of windows all might breaks in a day, so in other words, I want to know, based on all of time, on an average day, how many windows does all might break? Do you think it's better to have more days or less days if I'm trying to find, like, overall time, the most accurate possible number? It's better to have more days, right? The more data we have, the more accurate our conclusion is going to be. If you only take a very tiny time period, you're not going to have as full of a picture than if you take a bigger time period. For example, like, if you're trying to put together a puzzle and guess what the picture is, if you only have 4 pieces, you're going to have a harder time guessing what the picture looks like than if you have 10 pieces, right? So that means that we know this average of 25 windows from our second sample is probably a better representation than the 30 windows from our first sample, because we have more data the second time around than the first time around. But we don't want to just throw out good data. We're not saying that, yeah, this first time period has less data, so we're just going to ignore this 30. No, we still want to use that. That's still valuable data. We're not going to toss it out. We just want to make sure that the average that was based on more data, in other words, the average that was based on 6 days, has a bit more say in the final outcome than the average that was only based on 4 days. So when we combine them using the weighted mean, we get a number that's a little closer to the 6 days than the 4 days. If I had just averaged the 30 and 25 together, so a plain mean of the two, I would have gotten 27.5, exactly in the middle of 30 and 25. But we know that the 25 is probably a bit more accurate than the 30. So by doing the weighted mean, we get a number that's closer to our bigger sample. It's probably a bit more accurate. We're not tossing out the other data entirely, but we make sure that the bigger sample size or the bigger sample has more influence on the final result. Whew. Now, there is a problem with means. Nothing is perfect in this world, and means are certainly not an exception. Let's say we have an outlier. So we have a 5-day period. On day 1, all might broke 18 windows. On day 2, it was 22. On day 3, it was 25. On day 4, it was 30. And on day 5, all might broke 100 windows. We average that all together, we get an average of 39 windows a day. So a frequency polygon would look like this. Mostly he's in this range, and then on day 5, oh my gosh, he's breaking all the windows. That's insane. What this suggests is that this is an outlier. This one, day 5, is way unusual than the others. That's probably because something weird was happening. Maybe All Might was saving the world on day 5, and therefore he was causing more destruction than normal. Oh, sorry. You'll notice that the mean now of 39 windows is higher than 4 out of 5 of the actual days. The average has been pulled higher than it should be because of a single day. One single day has changed the average. So it's no longer representing 4 out of 5 of the days very well. It's really influenced by that 5th day. That's one of the problems with the mean. If there's one extremely high or extremely low score, that score is going to pull the mean higher or lower. If we got rid of that outlier, if we just changed that outlier to be equal to the highest score of the other normal data, our mean becomes 25. So that outlier really increased it. Windows George, I love this, not to get too distracted, but if you're familiar with the Spiders George meme, that is exactly the concept of outliers. Unfortunately, when I try and reference it in class, my students are too young, and then they weren't around for Spiders George, and I just feel really old. But exactly, Windows George. Windows George was an outlier and should not have been counted because you are using the mean to calculate your measure of central tendency, and Windows George has thrown off the mean terribly. It's no longer a good representation of most people. Anyway. Oh, to teach a stats class entirely using Tumblr's posts. Can you imagine? That would be wild. But yeah, by just getting rid of that outlier, by normalizing that outlier down to the second highest score in the data set, we lower the average numbers of windows broken by a full 14 windows a day. That outlier was making a huge impact on the result. So that's one of the problems with the mean. If you have an outlier, your mean is no longer going to be a good representation of the rest of your data because that outlier is going to heavily affect it. Then we have the median. So this is our second measure of central tendency. The median is the score that divides your data set exactly in half. Exactly half of the scores are higher than it, exactly half of the scores are lower than it. It is the precise midpoint of all of your data, and it's the equivalent of your 50th percentile. So 50% of people are below it, 50% of people are above it. You need at least ordinal data to calculate the median. You can do it with interval data, you can do it with ratio data, you need at least ordinal data, you cannot do it with nominal data. Why? Nominal data doesn't have an order. You could put nominal data in whatever order you want, so you can't find the middle. It's impossible. Everything else has an order, though, so you can do it with any other type of data. The way that you calculate the median is a bit complicated. It depends on whether you have an odd number of data points or an even number of data points. It's pretty rare that you're actually calculating the median, so I'm going to show you the cheesy way that I do it when I'm trying to do it by hand. I literally just, if it's an odd number, I start crossing out things on either side. Oh, there's the middle score. That's my median. Or let's say that we have an even number of scores. Let's say we don't have this 1 in here. I cross out 1 on each side. 2 and 3 are in the middle. In this case, if you have an even numbers of scores, we would just average these two. We'd find the point between these two. Our median would become 2.5. There you go. That's the median. That's how you calculate the median. If you're doing it on a big set of data, I would not recommend this method. I would absolutely recommend that you do it with some sort of computer program. So there's that. I will have that available when I post the PDF. Then the final measure of central tendency, we have the mode. The mode is the most common score in a distribution, the one that pops up the most in your data set. It is the so-called typical value. You can immediately identify the mode if you've got a frequency distribution or a histogram, because it's the tallest bar. It's the highest point. It's the most common thing. It's really easy to just eyeball it if you're looking at a graph, or a frequency distribution, I should say. The mode is great because you can do it on any kind of data. You can do it on nominal data, ordinal data, interval data, ratio data, doesn't matter. All of those types of data can have a mode. And in fact, it's the only measure of central tendency you can use with nominal data. You can't do anything else with it. You have to do the mode. So let's say you've got some data that you're trying to summarize and you need to pick. Should I use the mean, the median, or the mode? Well, that's a question. There's a couple of considerations. For example, technically speaking, the mean, the average, you should only ever use this for interval or ratio data. So data that has an order to it and also the units are all the same size. For example, average temperature or average height. This does not stop psychologists from doing it on ordinal data all the time. We calculate the mean for ordinal data all the time. We shouldn't. We shouldn't do that. But we do. You will not get by in psychology if you do not break the rules and calculate the mean of ordinal data. Clustering is a way off, but yeah, next week we're going to start talking about variability, and clustering comes into variability a fair amount. Look forward to that, but then there's ways you can get even more complex with clustering that I probably won't end up going over in this series of lectures. The mean is really interesting because it is affected by clustering. Like outliers to an extent are things that aren't sticking to the normal clusters, and they heavily affect the mean. But yeah, anyway, mean technically only valid for interval and ratio data, but in psychology and a lot of other things out in the real world, you'll see it used on ordinal data a lot too. The median is great for ordinal data. It's the preferred thing for ordinal data, technically speaking. So the median temperature, median food quality, that kind of thing. Median rent, median income. The mode can be used with anything. So the modal gender, the modal favorite movie, the modal whatever. And the mode is the only thing you can use if you have nominal data. So if you have determined that your variable's nominal, like color or hairstyle or genre or state or whatever country, you have to use the mode. There's no other choice. If it's nominal, you can't do anything else. So if you got nominal data, you're using the mode. Congratulations, there's your decision for you. Good job, good job. Can you take the mode on a continuous variable like temperature readings? Absolutely. Absolutely you can. You can take the mode on any type of variable you want. It might be difficult if you... So there are cases where a data set will not have a mode, and that's a case where no value is repeated. So if you say have temperatures from 10 different days and no 2 days have the same average temperature, there would be no mode. You wouldn't be able to calculate a mode, but like theoretically, if you have temperatures from 365 days and 2 days have the same average temperature, congrats, you can calculate the mode. So I guess it more depends on your data set. You can do it on any type of data or any scale of measurement. But yeah, with lots of precise decimal points, yeah. I mean, you can calculate the mode, but to have a mode, you would need data where 2 of those numbers are exactly the same down to the exact decimal point, unless you round them before calculating the mode, in which case you're losing some information. But you could do it, theoretically, if your data has at least 2 days that have exactly the same number down to the last decimal. But, you know, it's like a conditional thing. You need to have that case to calculate it. If you don't have that case, if your measurement is so precise that you don't have to, yeah, you can absolutely, that's right. That's another good solution. If you bin the data, so like give it ranges, 1 to 10 or whatever, you could also get the mode from that. That would be a way to get the mode from that data. Absolutely. So you probably wouldn't want to use the mode on that type of data for information, for like a point that we're going to talk about in a bit, but you could. You could. And binning would absolutely help with that. All right, so earlier we talked about skewed distributions. So skewed distributions are those distributions where maybe you have a lot of people scoring really low and very few people scoring very high, or the opposite, you have a lot of people scoring very high, very few people scoring very low. They're not symmetrical. If you fold them in half, they're not going to fold over perfectly. Like, the scores are being weird. This can affect which measure of central tendency you might want to use. If the distribution's symmetrical and unimodal, like the normal distribution, so that's lovely, it's very fun to draw, I recommend it. This lovely distribution where there's only one mode and it's perfectly symmetrical, obviously not how I drew it, but like, let's say you have a perfectly symmetrical unimodal distribution. All 3 of the measures of central tendency should spit out the same number. All 3 of them should give you exactly the same number. It shouldn't matter which one you pick, you should get the same thing if it's a perfectly symmetrical distribution. And that's great. But if the distribution's skewed, if it's not symmetrical, like these 2 in the upper right-hand corner of this slide, that's when things start getting a little weird. That's when it starts to matter which one you pick. So here's 3 different types of distribution and how the mode, the median, and the mean get. So here's a normal distribution that's symmetrical, unimodal. It's only got 1 high point, it's only got 1 mode, and it's perfectly symmetrical. The mean, the median, and the mode will all be the same number. So think of this bottom line as the x-axis, say from 0 to 100 or whatever. All get the same number. If you have a bimodal symmetrical distribution, so if you fold it over, it's symmetrical, but there's 2 high points, things start to get a little weird. Your mean and your median are still the same, but now you have 2 different modes. That's another weird thing about the mode. You might get multiple modes depending on your data set. If you have 2 numbers that are equally common, congratulations, you might have 2 modes. And then this is, I think, kind of what would happen if you have that really, really precise measurement to like many, many decimal places that you were talking about, Marlon. You might have a mean and a median, but because there's exactly the same amount of observations that have each number, so let's say there's only 1 day with each temperature, there's no mode, there's no most common number. You can still calculate the mean and median, you can't calculate the mode. So basically, if it's a normal distribution, in other words, it's symmetrical and unimodal, all of them will agree, doesn't matter which one you pick. If it's pretty much anything else, they start to disagree and things can get weird. You might have multiple modes, you might have no modes, the mean and the median and the mode all might start giving you different numbers. Things get really odd. So here's two examples of two skewed distributions. This one's positively skewed. We can tell because the tail is pointing towards positive numbers on the number line. And this one's negatively skewed because the tail is pointing towards negative numbers on the number line. Remember, it's the tail because it's the tail of the creature, the beast. The mode is still the highest point of the distribution. So the mode is still the most common thing. It's still going to be at the very top of the distribution. The median is still in the middle. Whoop. Median's still right in the middle. So it's still in the middle, but it's no longer at the mode. It's no longer at the highest point because now you've got some data that's way out here. And the mean, remember what we said about the mean being affected by outliers, extremely high or extremely low numbers? The mean has gotten pulled out towards the tail. So the mode is at the highest point, the median's in the middle, and the mean is more towards the tail. In other words, now all three measures of central tendency are giving you different answers. The same is true for a negatively skewed distribution. It's just the opposite order. The mode's still at the highest point, the median's still in the middle, the mean's getting pulled towards the tail. It's just, depending on which side the tail is on, they might go in a different. But yeah, if your distribution's skewed, they're all going to disagree. You're going to get different numbers depending on which one you pick, which can have some pretty interesting implications and consequences out in the real world. So just to check in, just to review, is this playset a positively or negatively skewed distribution? What do you think? Positively or negatively skewed? See, if this was a number line, negative numbers would be on this side, positive numbers would be on this side. Tail is pointing towards positive numbers. It'd be to the left. So negatively, since we put negative x to the left. See, this screws me up too, and this is why I have to remember it this way. Positively skewed distributions, the tail is what determines it. I always thought it was like, oh, most numbers are on the negative side, so it's negatively skewed. Nope. For some reason, whoever named it didn't think of it that way. They say, this is a positively skewed distribution because the tail is pointing towards more positive numbers on the number line. It's a pain, isn't it? It's not intuitive to me. I know, most of my students, when I'm teaching this, will, be like, oh, yeah, that makes sense. And I'm like, does it? I'm trying to teach it in a way that makes sense, but it's not what I would have, how I would have named it. Yeah, this is a positively skewed distribution. Well, it's not a distribution, but if it was, it would be positively skewed. Sometimes people just name things in ways that I don't necessarily agree with, but we've got to put up with it. For the sake of mutual intelligibility, we are stuck with this being positively skewed. All right. So, I actually usually use this. For this, I usually actually use naming things is the hardest thing ever. So for this, I usually use a graph of household income in the US, but that can get a bit depressing. I'll talk about that as an example later, because I think it is a good example for how these things get weird. Oh, sorry. Well, you have it now, so if this comes up in any future classes, yay! Oh, well, this will be here. Anyway, this time we're talking episodes of anime per series. So 1, 2, 3, how many episodes were in that anime? Here on the x-axis, we have the number of episodes. Here on the y-axis, we have the number of anime that had that amount of episodes. And I had to make this a grouped frequency distribution, as you can probably guess. I think, what did I make the breaks? Was it? I think I probably make the breaks 20 or something like that. 20 wide bins or something along those lines. maybe even 50, I'm not sure. Either way, taller bars indicate more anime that are that length. Shorter bars indicate fewer anime that are that length. First things first, is this a positively or negatively skewed distribution? This is a very skewed one, by the way. I should set up a poll, actually. Yes, I like polls. Polls are my favorite. Positively or negatively? Please excuse the typos. The I key on my keyboard is broken, so we're just gonna have to cope with that. Please don't judge me. It's my keyboard, I swear. Giving it another few seconds. Oh, I do not do chemistry. I do psychology. Yeah, I don't know anything about chemistry. I haven't taken chemistry since high school. So you'd have to look elsewhere for that, unfortunately. All right, you are all correct. This is a positively skewed distribution. The tail is pointing towards positive numbers on the number line. So yep, this is a very, very, very positively skewed distribution. Most things are in here. Very few things are all the way out here. We would look something like that. Now, if we had to guess, anyone want to guess roughly what the modal number of... Here, let me check just to be sure about the breaks on this one. It looks like I don't have that noted down, but I think the breaks are roughly 20. So this would be like... Oh, no, spoilers. So the first bar would be roughly 1 to 20 episodes. The second bar would be roughly 21 to 30 episodes, and so on. What do you think the mean number of episodes an anime is? What do you think, based on this graph? Most animes have 0 episodes. Because they haven't been made yet, because our future is bright and there is so much more anime on the horizon? Is that what you're getting at? By the way, you do not have enough information to actually calculate this. I'm just looking for wild guesses. So if this is like 1 through 20, you can give me a range. This is 21 through 30. This is 31 through 40. 41 through 50, yada, yada, yada. I've already shown the answer by accident, so why not? The average length of an anime is 35.91 episodes, according to this data set. So based on the anime in this data set, the average is 35.91 episodes. The median is 24 episodes, so 2 cores. You know, like 2 anime seasons. There you go. And the mode is 12 episodes. That's a pretty big difference. That is a huge difference between the mean, the median, and the mode. So let's say I'm recommending, I want to get my friend to start watching anime, and they want a pretty low commitment. They're like, I don't know if I like it yet. I'll watch one series. I don't even know if I want to have time to watch one series. How long is the typical anime? Do you think I'd want to tell them the mean, the median, or the mode? If I have a friend who says they don't know if they have enough time, which do you think I'd tell them? Probably tell them the mode, right? If my friend doesn't have a lot of time, I want to make it seem like anime are pretty short. on average, right? And the mode has a pretty low number. That's 12 episodes. Let's say I have a friend who's looking for something really long to watch and I want to get them into anime, and they're like, I need series that go on forever, that I can count on, that I can binge for weeks at a time. And you're like, well, anime's just the thing. The typical anime is, you might choose the mean, right? The typical anime is nearly 36 episodes long. The average anime is 36 episodes long. When really, actually, most anime are more like 12 to 24 episodes long. You've just got things like freaking Detective Conan and One Piece as outliers dragging that mean up, right? So it depends on what you're trying to accomplish. And you see this with, so like I said, I typically use the average income for families in the US. The average income in the US, at least from the data I use for that is from 2010, I think. And the average income in the US, the mean is something like 75,000. The mean is something like 75,000. The median is more like, I think it was like 45,000. And the mode was more like 20,000. So depending on which measure of central tendency you pick, you're going to get a very different idea of how much the average or the typical household in the US is making in a given year. And politicians take great advantage of this. If a politician's really interested in getting, if raising taxes on the wealthy and giving more money to welfare programs and things like that, they would probably choose the mode to describe the typical income in the US, because it makes it seem like Americans on average, like the typical American family is making a very small amount of money a year. If you don't want to raise taxes, if you want to cut welfare programs and things like that, if you're describing the typical American household income, you'd probably want to use the mean, because that makes it seem like most families are pretty well off. This is what they mean when they say like lies, damned lies, and statistics. You're looking at exactly the same data set, but depending on which measure of central tendency you use, it can be telling a very, very different story about what's going on in there. You can report statistics in many different ways, and depending on how you report it, people might draw wildly different conclusions from the same data. So if somebody tells you the average or the median or the mean, or the average, the median, or the mode, pay attention to which measure of central tendency that they're using. Especially if it's something with a very skewed distribution, with, say, most people scoring very high or most people scoring very low, with very few people scoring very high and very few people scoring very low. Pay close attention to which one they're using, because they might be trying to manipulate you. They're telling the truth, but they're telling a certain version of the truth that fits what they want to convey. So, general summary of properties of these things. The mean should technically only be used with interval and ratio data, though a lot of people will also use it with ordinal data. The mean doesn't necessarily equal any given number in your set of numbers. It doesn't necessarily equal a real data point in your data set. And it's heavily influenced by outliers. If you've got an extremely high or extremely low score, the mean is going to be dragged out more towards that score and may not really look a lot like the so-called typical score in your data set if you have a skewed distribution. So you got to be careful with that if your distribution is skewed. If your distribution's symmetrical, there's an equal number of people above and below the mean, you're fine. The median can be used with ordinal, interval, and ratio data guilt-free. It's not nearly as affected by outliers, which means that if you've got a distribution like this one, or if you have a distribution like, say, the average household income in the US, and it's something that's heavily skewed, the best representation of the so-called typical score in that data set is probably going to be the median. You should probably rely on the median for that. You might be asking why I would say, why not the mode then? Why wouldn't you use the mode for a skewed data set? Well, there's a reason for that. The big advantage of the mode is that you can use it on any type of data. It is the only measure of central tendency you can use when you have nominal data, which doesn't have an order, which is great. Its disadvantage, though, is it's really unstable. Let's say I try and get, say, the average income or the average number of episodes, and I get like 5 different samples. So I get like 5 sets of 20 families or 5 sets of 20 anime each. The mode might vary wildly from sample to sample. It might change a lot. It's not very stable. It's really affected by like differences in samples. So if you're trying to get a consistent idea of the typical value, it's the most likely to be inconsistent. So you probably don't want to use the mode that much. Typically, the mode is really only used for nominal data, even though you can use it for most, because it varies a lot. It doesn't stay the same. The median and the mean stay fairly the same. The mean is the most consistent across different samples. Now, which one are you going to pick? Which measure of central tendency you want to do? It depends on what you're trying to accomplish. So, like I said, statistics can be used for agendas, and you shouldn't pick the measure of central tendency that you're picking to try and make a certain point. You should just be trying to represent the typical score, but people will choose the one that they want depending on what they're trying to accomplish. So let's say you work for a company. This company has 9 employees. 9 of these employees make $35,000 a year, and they have a supervisor who makes $150,000 a year. If, say, your friend is applying to work at this company and they want to have a realistic idea of how much they're going to make at this company, which measure of central tendency do you think you'd use? You want to give your friend a realistic idea of how much money they're going to make. Is there a measure of like ratio of median to mean to qualify data set outliers? Oh, quantify? There are ways of quantifying outliers, and they typically don't involve, at least in my experience, comparing the median to the mean. I don't actually have that in the slides, so I might as well mention it. Usually it's based on the variability of the data set. So there's this concept called the standard deviation, which we're going to talk about in next week's lectures. But it says, on average, how far away are scores from the mean? So like basically how clustered are the scores or how spread out are the scores? And if you have a handful of scores or like 1 score, 2 scores, 3 scores that are very, very, very far from the mean in units of standard deviation, they're much further from the mean than average. Those are what we'd typically call outliers. So that's one of the major ways of detecting them is if they are very far away from the mean, let's say 3 standard deviations, 3 units of distance away from the mean, at that point we might consider them an outlier. There's a bunch of different ways of determining whether something is an outlier. There's no standardized ways yet, and I'm not aware of a way that compares the median to the mean, but that is an interesting way of thinking. Say. I think it's because we're typically not interested in if there are outliers. We're more interested in which data points exactly are the outliers, if that makes sense. We're not trying to say yes or no, are there outliers? We're trying to say, assuming, like, if there are outliers, exactly which numbers are the outliers, which numbers count as outliers. So that way we can figure out how to deal with those numbers. That makes sense. So I think that's why I haven't seen anyone do it that way. But yeah, there's a lot of different opinions on how you should determine what an outlier is, and those can influence your results depending on which method you pick. There's a lot of discussion around that. It's a whole field of a whole bunch of statisticians yelling at each other. Honestly. Anyway. If you're trying to get your friend a realistic idea of how much money they would make working at this company, would you use the mean, the median, or the mode? And there might be more than one correct answer here. I'm going to put up a poll. Use the mean, median, or... Go. We have 9 people making 35,000 and 1 person making 150,000. Wonder what I would pick. Ooh. Got 2 different opinions. And like I said, there might be multiple correct answers for this one. So just because you 2 disagree doesn't necessarily mean that one of you is wrong. Gonna give it a few more seconds. Okay, let's end it there. You are both right. Yes, in this case, sorry, both the median and the mode would give you exactly the same answer. They would both tell you 35,000. So they're both giving you the same answer. And both of those, I think, are pretty realistic. They're giving you a pretty realistic idea of exactly how much money your friend would make, because 9 out of 10 of the employees are making that much. Both of those are great choices in this scenario. Now let's say you want to be a jerk. Let's say you're the recruiting officer from this company and there's somebody you really, really, really want to hire. And also you don't have morals. You don't really have much of a moral compass. And this person wants to work for a company where they can make a bit more money. So the idea here is you want to recruit this person. You want to give them a true statistic. You want to give them real numbers based on real data about how much they'd make at this company, but you really want to make sure that they pick your company to work at, that you think that they think that they're going to make as much money as possible at your company. Would you pick the mean, the median, or the mode? And again, we're pretending we have no morals for this one. In a world where we have no moral compass, which would you pick? Hmm. We want to make them think that they're going to make the highest salary possible. We're still using our real data of 9 people at 35,000 and 1 person at 150,000. Hmm. See one of you's being very sneaky with statistics. Mm-hmm. All right, I'm gonna give it a few more seconds just in case. All right, you are correct. If you really want them to think that they're going to make the most amount of money possible, you would pick the mean. We have an outlier here. Yep, speaking of outliers, we have this one person who's making $150,000. I'd consider that an outlier. That is much higher than everybody else, right? I think if you actually calculate the mean out or something like that, you would end up telling that person that they'd make that the average salary at your company is about $45,000 a year, which obviously they're probably not going to make that. They're probably going to be another one of these people making $35,000 a year. But because you've got this one supervisor making $150,000, that unusually high score, that outlier is pulling up the mean, you can give them a real statistic if you are kind of a mean person and say, hey, the average salary at our company is $45,000. So yeah, if people tell you the average salary of something, it might be good to see if you can find out what the distribution of salaries looks like, because it could be that most people are making nothing, and then you have the CEO that's making like billions of dollars, and that's just pulling the average up. This is why it's called the mean, because it can be used for evil when it's in a skewed distribution. Perhaps, and not the nice. Oh, there goes my evening looking up the etymology of the word mean. But hey, if that helps you remember that the mean can be very misleading, I would call that a success. Anyway, yeah, measures of central tendency and frequency distribution. That's what I've got for today. I'm now open to any questions, comments, concerns, anything that you might have about this lecture and things like that. Next week, we will be talking about variability. Oh, yeah, I also had a question for y'all. I put up a poll on the channel. So far, I've been editing these things from my normal lectures to include more anime examples, because I kind of started out as like an psychology of anime channel, but that takes a lot of time, and sometimes I feel like it's probably not as informative for people who just want to learn about stats and maybe aren't as into the anime aspect. So I was wondering, yeah, I put up a poll on my channel if it would be preferable to stick with changing things to anime examples, to use solely psychology examples, some mix thereof, or just whatever random examples I think fit best in a given place. So yeah, you can go over there and vote in that if you have a strong opinion. But other than that, I'm happy to take any questions that you might have. I will do my best. And if you don't have any questions, that's fine too. Or if you come up with them later, feel free to drop them in the comments section and I'll get to them as soon as I can. Whatever works. All right. I think it seems pretty quiet, and it's almost my cat's dinner time. I wouldn't want to keep him waiting. So, thank you all for coming in. It was great talking to you all, and I'm looking forward to seeing everyone who can make it to next lecture. If you have any questions or anything like that, feel free to drop them in the comments section, and I will see you next time. Bye, everyone! And thank you for coming. Thank you!